Okay, so we can start. Welcome back. So last time we gave a brief introduction on nonlinear systems, and then we talked about some basic definitions on stability, which were all from the theory developed by Lyapunov. And so remember, we talked about what we called an autonomous system, which was basically a time-invariant nonlinear system, and a non-autonomous system or time-varying system. Of course, when we give general theorems about these systems, they will apply to linear systems x dot equal ax as well, of course, but you can say more precise things for linear systems, okay? Similarly, if we give general results on non-autonomous systems, they will also apply to autonomous systems, which are a particular case, right? But of course, they'll be more precise for autonomous systems, okay? So when we say non-linear, we mean not necessarily linear, right? And when we say non-autonomous, we mean not necessarily autonomous. Okay. So it's just more and more general, if you want. So we define what we meant by an equilibrium point, focusing until further notice on autonomous systems. So an equilibrium point is a state such that if you start there, you stay there, which, if we take this equation, x dot equal f of x, means that f at this equilibrium point is 0. And we said that, contrary to the case in general in linear systems, you don't have just one equilibrium point, because this equation by itself, in general, defines a whole set of equilibrium points, which could be a discrete set, a continuous set, all sorts of things. We said, for instance, if we had a pendulum, we had equilibria here, and we had equilibria there. And if we had stiction, we had even more, right? A continuous set of equilibria. So when we talk about an equilibrium point of a nonlinear system, in general, it's not unique. And therefore, when we're going to go to the next step, which is to try and say something about what's the qualitative difference between here and there, okay, which obviously has to do with some form of stability, okay. When we do that, of course, we're not going to talk about the stability of the system, but we're going to talk about the stability of an equilibrium. For instance, is this equilibrium stable, or is that equilibrium stable, and so on. Okay. So then we gave a number of definitions of stability, and these definitions at the beginning looked rather technical, but we tried to make a point to explain that they correspond to very practical concerns, okay, and that the only reason you hadn't seen them before in a linear control course is that in a linear control course there's not this gradation of form of stability. Basically, either things are strictly stable, in which case they're globally exponentially stable, or they're unstable, perhaps marginally stable. So we said we would talk about stability in the sense of Lyapunov. So remember, stability in the sense of Lyapunov had to do with saying for any ball of radius capital R, there exists a small ball of radius small r, such that whenever you start in the small ball, you never get out of the big ball. We said it was some kind of continuity condition, and from a practical point of view, it means that you can contain the system as close as you want to the equilibrium by starting close enough to it. Okay? So if the as close as you want is defined by this capital R, and close enough to it is defined by the corresponding small r. Okay? And of course, you can compute that, right? Because, well, or at least as we'll see, you can compute that because we'll have tools to do that. Okay? Then we have asymptotic stability. So asymptotic stability, we said, was stability plus an extra condition, namely there exists a particular radius r0 such that when you start within r0 of the equilibrium point, or of course within anything smaller than that, you actually get back to the equilibrium point. Okay, so that was asymptotic stability, and we explained why asymptotic stability had an explicit requirement of stability in this definition. Okay, so asymptotic stability is stability plus the fact that you go back to the equilibrium. Okay, from a practical point of view, it says the system does something, right? The system goes to a point, goes to an equilibrium. Okay? We talked about global asymptotic stability, which was the same thing, but when R0 was infinity, in other words, starting anywhere, the system went back to the equilibrium point. Okay? We talked about exponential stability, which also was defined in some region and introduced an extra notion, which was a notion of time constant. Namely, you knew how long it took the system to go back to the equilibrium point. Okay, it was bounded by some decreasing exponential. Okay, and we said there was a scaling factor which basically just shifted the time. Okay, so for instance, in about this shifting delay plus maybe 3 time constants, you are close to the equilibrium point, or 5 time constants or something like this. And we had global exponential stability, which was again R0 equal infinity. Okay. Namely, starting anywhere, you went back to 0 with this known time constant. Okay, and we said for exponential stability, there's not the subtlety that you have to impose stability first because it automatically implies it, and we'll show this in one homework. Okay, and we finish by saying what I just mentioned, which is all of these correspond to very practical concern, being able to contain the system, for instance, in the region where the model is valid, okay? Being able to say the system goes somewhere, being able the system goes somewhere from a large region, from starting anywhere in a large region, being able the system goes somewhere within a certain time constant. Okay, so these correspond to very practical concerns. But of course, if you have x dot equal ax, well, if A is strictly stable, then this equilibrium x equals 0 is globally exponentially stable, and otherwise you have marginal stability or instability. Okay? And we also said that in the global case, you could talk about stability of the system rather than stability of a specific equilibrium point, because if you had this global asymptotic or exponential stability, it meant that starting from anywhere, you ended up at the equilibrium point, so there could be no other equilibrium points, right? Because if there was another one, then by definition, you would stay there. You would not end up here. So in the global case, whether it's asymptotic or exponential, that's a case where you can talk about the stability of the system, the global stability of the system, because you're sure there can be only one equilibrium point. Okay. Questions about that? Okay. Good. So what we're going to do or start to do today is talk about theorems which allow you to show whether the system verifies some of these properties, in particular stability, asymptotic stability, and global asymptotic stability. But before we do that, we're going to just ask a rather natural question at this portion in the course is, now that you've told us that all the real systems are nonlinear and you have to use all these tools, what should we really board this airplane, going to Europe? Because we know it has been entirely designed using linear techniques, right? Or at least, until recently. And so, what can we say about that, okay? So there is a part of Lyapunov theory which is sometimes completely incorrectly called the first method. It's not at all the first method. He never called it that. Actually, in Lyapunov theory, it was a footnote because Lyapunov was a mathematician, so he made a quick remark about this. And But so the question is, what can we say about linearization and local stability? Okay, so that's the first thing we'll look at. Briefly. And sometimes we'll prove theorems in class, sometimes the proofs will be in the book, or sometimes I'll say, well, we'll prove a stronger version of this theorem much later in the course, and this is the case here. We'll prove a much stronger version of this theorem later in the course. So, all right. So let's look at this autonomous system, right, which has an equilibrium point at 0. Okay. So we can do a Taylor expansion of f of x, this function, the smooth function, unless otherwise noted, we'll assume everything is smooth, which means you can take as many derivatives as you need and they're continuous. Okay. So not more than you need, of course, but just as many. Whenever we write a derivative, it exists and it's continuous and it's fine. So we can do an expansion, and if we do an expansion, we'll find f of 0 plus df over dx at x equals 0 times x minus 0 plus higher order terms, HOT, higher order terms. All right? So so that's a Taylor expansion. So what is, by the way, this df over dx? It's called the Jacobian of f with respect to x. And of course, is the matrix, if f1, f has component f1, f2, fn, right, is the matrix df1 over dx1, df1 over dxn, dfn over dx1, dfn over dxn, and here somewhere in the middle, dfi over dxi. Okay. So that's the Jacobian, right? The matrix. So think of it, right? So suppose you see this first row as a vector, right? What is this vector? The first row of this Jacobian. Well, it's just the gradient of f1, right? The first component of f with respect to x, right? So basically, you have f of x, which is a nonlinear dynamics. It has components, f1, f2, fn, right? If you take the gradient of f1 with respect to the state, you put it in a line, and you get the first line of the Jacobian. The gradient of f2 with respect to the state, you get the second line, and so on. Okay? So that's the Jacobian. So we are at an equilibrium point, remember, right? So f of 0 is 0, so this term doesn't exist. This term, anybody has a creative notation for this term? Well, we'll call it A, right? This is the A matrix, right? It's the Jacobian of the nonlinear system at x equals 0. X minus 0 is otherwise known as x, right? And then plus higher order terms. Right? So the linearization or linear approximation is x dot, we'll put this not to confuse this, right? So we'll use this notation, x dot equal ax. That's the linearized approximation. And that's an approximation which is obtained by basically neglecting all the higher order terms. Okay? And this approximation is perfectly well defined. A is well defined because a Taylor expansion is unique, right? It has to work for any x in the neighborhood and so on, so it's unique. Okay? So that's the linear approximation. Now, of course, you can do the same thing. Let's say if you had a system, x dot equal f of x and u, right? A state and then some input, perhaps some control input. All right? So if we assume that f of 0 and 0 is 0, okay, so we're at an equilibrium, let's say x equals 0, we're at the point x equals 0, and the controller is also 0. Then, of course, we can do the same thing, df over dx, now at x equals 0, u equals 0 times x. And df over du at x equals 0, u equals 0 times u, plus higher order terms. Okay. So this matrix, suppose x, the dimension of the state is n. What's the dimension of this matrix? df over dx. It's n by n, right? Because, you know, x dot is equal to f of x, right? So f has the same dimension as x dot and therefore of x, right? And suppose there are m inputs, you know, the dimension of u is m, okay? So what's the dimension of this matrix? n times n, okay? Where m is dimension n, and u is of dimension m. Okay? And of course, this matrix will still call A, right? And obviously, this matrix will call B. Right? So the B matrix is the linearization of the dynamics, right? At x equals 0, u equals 0. And because the linearization is unique, you could keep going. So for instance, if you have u of x, which is g of x, which is 0 plus dg over dx times x plus higher order terms, then you could call this matrix capital G. Right? So that would be u equal gx would be the linearization of u equal u of x, the control law. Okay? And if you plug in this linearization in there, right, you're going to get x dot is equal to a plus bg times x plus higher order terms. Right? So in other words, this is true in general, right? Now you say, suppose I choose a particular, you know, seeing x and u as input to this function f, right? If you now choose a particular controller, u of x equals some function g of x, right? Which is 0 at 0, for instance. Then you can again compute the Jacobian of that function with respect to x. You can call it g or whatever you call the gain matrix, usually k, right? G or k, whatever you like to call it. And of course, you can plug it in there and you'll get a plus bgx plus higher order terms, which is exactly what you would have gotten if you had put directly u of x here and just did the expansion with respect to x, because the expansion is unique. Okay, so basically in math, you always get back on your feet, right? So the expansion is unique, right? So you can do it this way, do the approximation first and plug it in the approximation, or put u of x in there and do the expansion and you'll get the same result. Okay, so just to remind you of Jacobians. Now, suppose I'm given a system, let's say, do something like this? Maybe I'll erase this. Suppose I'm given a system x dot 1 is equal to x2 square plus x1 cosine x2. X dot 2 is equal to plus x1 sine x2. Okay, so suppose you have this system. And, suppose it's a homework or whatever at this point, and you say, and you're told, well, consider a system. Try to say something about it in terms of stability or whatever, perhaps using approximation. Okay, so try to say something perhaps approximate about it. Okay. So, since we haven't done anything else yet, you might say, well, I'm going to linearize and see what I can say, right? So, first of all, if you want to linearize, you have to find an equilibrium point. Okay. So, what's a reasonably obvious equilibrium point of this system? Sorry, it should be x1 plus 1. What's a reasonably obvious equilibrium point for this system? 0, right? So, x equals 0 is an equilibrium point. Okay, not necessarily but certainly an equilibrium point, right? If you have x1 equals 0 and x2 equals 0, then you have x dot equals 0. Okay, so that's clear. Now, if you want to compute A, you could do this, right? You could take this, compute the Jacobian, and then compute the result at x equals 0. Okay, so you could do this, just apply this. In a sense, that would be a possible thing to do. Now, it would be, especially if it's an exam or especially actually conceptually, it would be a big waste of your time, okay, to do it this way. Why? Suppose you want to linearize the system, get the approximation x dot equal ax. In a concrete example, well, concrete, at least mathematically concrete example like this, right? Do we really need to compute the Jacobian, which is basically taking all these gradients, right, and then apply that x equals 0, or can we do anything faster?
Just expand it and ignore the higher order.
Exactly. So he's saying, of course, I mean, most of you know this, right? Another way to do this is to just expand this dynamics and ignore the higher order terms. Now, why is this okay? Because A is unique, right? Because this expansion is unique, right? Otherwise, you might get something, right? But it might not be what you're looking for, right? But A is unique. You know that this is unique because it has to work in anywhere in the neighborhood and so on, right? So this expansion is unique. So whatever you find which looks like this, some linear terms and then some higher order term, you'll have A. Okay? So of course now it becomes very easy, right? So x dot 1 is equal to x2 squared. So what do we do with x2 squared? We throw it out, okay? So x dot 1 is approximately equal to 0 plus, what do we do with x1 cosine x2 in the vicinity of 0? It's just 1, right? So x1 times 1, okay? So we get x1. What about x dot 2? Well, x dot 2 equal x2. We're not going to throw away that term, right? x1 squared plus x1, what do we do? x1, right? So x2 plus x1. x1 sine x2. Well, you don't want to throw away things too fast, right? So x1 sine x2 is approximately x1 x2, right? Because sine x2 is approximately x2 plus higher order terms, right? So this will give you x1 plus x2. Right? And therefore, the A matrix will be what? 1, 0, 1, 1. Right? Okay. So if you have an explicit set of equations and you need to linearize it with respect to an equilibrium, right, just go ahead, expand, right, and then throw away higher order terms. If you need to prove things about, linearization and other things, then of course you want to keep this general form. Okay? And later on in the course, we'll talk a lot about, how much information is there not linearization from linearization not at a point, but linearization everywhere. Okay, and we'll see that with linearization everywhere, actually, you can get a lot of information on the system. Okay, questions about that? Just to remind you about linearization, we still haven't given any result or whatever. It's just, just to remind you about linearization. Okay. So now, question? Okay, so we have theorem 3.1. Lyapunov's linearization, sometimes called method, all right? But it's, again, it was just a footnote in Lyapunov's work. So here we are our system, x dot equal f of x, with an equilibrium point at 0. And we linearizing this system. So we're saying, okay, so let's consider the linearization of the system, ax plus higher order terms. And suppose now we look at this linearization and we just look at the approximate system x dot equal ax. We can look at the stability of the approximate system. Right? We can look at the stability of x dot equal ax. Okay? And so Lyapunov's question was, suppose we look at the linearization of the system, what does it tell us about the real system? What does it tell us about x dot equal f of x? And of course, if the answer was absolutely nothing, you should cancel your plane ticket, right? But of course, Lyapunov's linearization result says, well, linearization tells you something about the real system. Okay? But as you'll see, this something is not really explicit. Okay? So what does it tell you? It tells you, with a slight abuse of notation, if A is strictly stable, so in other words, if what you would call Hurwitz, right? So if A is strictly stable, in other words, if the system x dot equal ax, the approximate system x dot equal ax is strictly stable, in other words, if all the eigenvalues of A are strictly in the left half plane, okay? Are strictly in the left half complex plane. They all have negative, strictly negative real parts. Okay. then this equilibrium point is actually asymptotically stable. But just asymptotically stable, okay? So we don't know, for instance, R0 or whatever, right? We just know it's asymptotically stable if we just use this theorem. Right, so we don't know if, if you perturb the system within something which is not even within measurement range, it won't be true anymore, right? It just says it's asymptotically stable. There exists some region, an R0 such, right? Okay? If A is strictly unstable, which means, i.e., at least one eigenvalue of A strictly in the right half plane, then x equals 0 is unstable. You might tell me, well, you haven't defined unstable. Well, that's very true. Unstable is not stable. Okay? No, it's you have to be precise, right? So it's not stable. Okay? So in other words, it's not stable in the sense of Lyapunov. Okay? So in other words, it's not even true that you can arbitrarily bound the system by starting close enough to 0. Okay? So it's unstable, meaning not S. If A is marginally stable, so as you know, it means it has all its eigenvalues in the left half plane, but perhaps some just on the j omega axis, on the V imaginary axis, right? So it has all its eigenvalues in the left half plane, but perhaps some on the imaginary axis. Then, any guess? Who knows, right? That's the mathematical statement, right? So we haven't proved this here. We'll, as I said, later on in the course, we'll prove a much more, powerful version of this. In particular, it's exponentially stable in the first case, and so on. But intuitively, why does this make sense? Because it says, this is kind of by continuity, right? You have x dot equal f of x. F of x is equal to ax plus something. Right? So in a small enough region around the equilibrium, the something is small. Right? And therefore it's kind of a tiny term, and so what dominates the behavior is x dot equal ax. Okay, that's not a proof, it's just a hand-waving intuition, if you want. Okay? So this, this result says, this is kind of a continuity result. It says, well, if you start really close, then it's okay. Right? And of course, you can see this from a numerical point of view as well, right? When is sinus x equal to x? Well, you have a reasonably good idea of what you mean by that, okay, given the kind of precision you want. Okay. Now, why did I say who knows? Because suppose that we take again our toy example. We said it's a kind of simplest possible example of an underwater vehicle or parachute or something like this, right? So v is velocity, the state is velocity, right? And this is the equation, right? So this system, as you can guess, will be asymptotically stable, right? In the vicinity of zero velocity in that case, okay? So we'll show this much more precisely, but is just a system with drag, right? And so if you give it an initial velocity, it will end up, stopping right, because of the drag. Okay, so one can show this. We haven't shown this, but intuitively, physically, right, it's fairly obvious that this is going to work, right? Now, what's the linearization of the system? The linearization, sorry. Is v dot equals 0, right? Because this drag term is a higher order term. Right? So when you linearize, you throw away the higher order terms, right? There's no linear term. So the linearization is v dot equals 0. So we are in the case where we are in the third case of the theorems who says who knows. Okay? Now I'm trying to make you understand why it says who knows. So this system happens to be asymptotically stable around v equals 0. Its linearization is equal to 0. Can you give me another system which has the same linearization but which is obviously unstable? Right. So suppose you now consider the other system, right? V dot minus v hat v, right? So think of it. You have a vehicle now. It's subjected to a force. And the larger the velocity, the larger the force in the same direction. Right? So it's minus drag, right? Well, obviously this is going to be unstable, right? And again, we can show this, but you don't need much imagination to understand this, right? Right? Whenever you have a positive velocity, you apply a positive acceleration proportional to the square of the velocity, right? So that's not going to take you anywhere calm, right? What's the linearization of a system? The same, right? It has the same linearization. So in other words, when the system is marginally stable, it means the linear part is not where the action is. It's at the higher order terms, right? At least for the corresponding poles, right? So when the system is marginally stable, it says, the action is in higher order terms. And by definition, you throw away the higher order terms. So that's where who knows, right? In the last case, A is marginally stable, you throw away the information. When linearizing, you threw away the information which would have told you something about stability, right? As this case shows rather easily. Questions about that? Okay. So again, we haven't shown this, and we'll show a stronger version later on in the class. Questions? Okay. So, questions? No. So it's now time to move for the main result of all of this, okay, which is Lyapunov's direct method. And I give you again the section references in the book if you're interested. And so Lyapunov's direct method is a way, as we'll see, a very simple way, but at the same time a subtle way, to determine stability, asymptotic stability, and global asymptotic stability for a given system x dot equal f of x. Okay? Now, this has become, a kind of a pillar of nonlinear systems. So when you hear about Lyapunov stability theory, actually, people may mean another 127 theorems, okay? But these are the main ones. Okay. So what was Lyapunov's idea? Well, again, Lyapunov was a mathematician, but, as many good mathematicians, he had a very strong sense of physics, and actually, a lot of questions in mathematics come from physics, of course. And, he said something like, maybe not with exactly this example, but something like, well, suppose you take a pendulum like this, and there's friction, and it's going to stop, right? And if I do this, the same is going to happen. And if I put kind of wings here and do this, the same is going to happen. So you see, if we take our model, which we wrote last time, you know, with sine theta and so on, right? Well, we could say, well, how can we show this? Well, we can assume that we move the system a little, but what does a little mean is not clear. Certainly not this, right, but a little. And we linearize the system as we look at the eigenvalues of the linearized system or the poles, right? And we can show, well, it says that if you move your system a little away with a little velocity, and you're not quite sure what you mean by small in this case, right? Then it will come back. And Lyapunov said, well, that seems like an extremely contrived way to look at the problem, right? The obvious reason why the system goes there is that it starts with finite energy, and this energy keeps being dissipated, right? And the system stops when there's no more energy to dissipate, right? And of course, it has nothing to do with small angles, right? It could start from here. Sine theta is certainly not equal to theta there, right? And it has nothing to do with small angles. It has to do with the fact, and linearization, right? It has to do with the fact you start with finite energy, and this energy keeps being dissipated, okay? And Lyapunov, putting back his mathematician hat now, was said, well, you know, wouldn't it be nice to take a general system x dot equal f of x and somehow build a scalar summarizing function like energy, but perhaps something a little more, where we had to put a little more thought in, such that from the behavior of this scalar summarizing function, the scalar energy-like function, we conclude things about stability of the system in a nonlinear sense. Okay? So that was Lyapunov's idea, okay? The idea of inspired by energy or entropy in another context, or, you know, basic fundamental concepts of physics summarized by scalars, okay? Typically positive scalars. How to build a general mathematical theory of stabilities of systems like x dot equal f of x. Okay, so that was Lyapunov's idea. And it was a brilliant idea, which you find in many different forms today. Okay. So before we get into this, let me just remind you of some basic, undergraduate, actually, a freshman, physics calculation, okay, or mechanics calculation. So suppose you have a mass spring damper system. So you have a nonlinear spring. And you have a nonlinear damper. And you have a mass, okay? Incidentally, in electrical circuits, you can have easily the equivalent of a nonlinear mass, and so we'll have a homework about that. You can have that also in mechanical circuits, but it's more complicated. So suppose we write the dynamics of a system, so it's mx double dot, right? Suppose that we start, we have the x-axis here, which we initialize somewhere, okay? This is the x-axis. So mx double dot, we said we have a nonlinear damper. Since we've already played with things like viscous friction, we'll put viscous friction, doesn't have to be. And, or drag, right? And we'll put a nonlinear spring. Okay, so this is damper. And this is spring. And that, of course, is equal to 0. And we're not going to really look at stability or whatever. We're just going to do energy balance for this system. You know, some basic things about energy just to remind you of this basic computation, because it's computation we're going to see several times in a more general mathematical context. Okay. So, incidentally written this way, this system has an equilibrium at one equilibrium at least. Well, at x equals 0 and x dot equals 0, right? Right. Incidentally, we'll often use this slight abuse of notation, okay, so that if you have position and velocity, we'll call the whole state x this way, okay? And of course, when we underline, we mean vectors. So we have this equilibrium here, okay? Now, so what's the total mechanical energy of this system? Well, it's the sum, of course, of the kinetic energy and the potential energy. So what's the kinetic energy? Well, 1/2 of mv squared, right? So it's 1/2 of mx dot squared. And what's the potential energy? Well, first, where does it come from? Well, just from the spring, right? Because we have, this is a horizontal system, right? So it just comes from the spring, right? And so the potential energy we could write as the integral from 0 to x of the spring term, which is k0y plus k1y cubed dy. Right? It's like the work, right? So the potential energy is the integral of the spring term from 0 to x, right? So if we put everything together now, we get 1/2 of mx dot square plus k0 x squared over 2 plus k1 x4 over 4. Okay? So that's the total energy of the system, the sum of kinetic plus potential. Potential is the integral from 0 to x of the spring terms times the variation. And so we get this. Okay? All right. Now, suppose we call this quantity v of x here. We can make a few remarks about v of x at this point. What can we say about this? Well, first of all, it's a scalar, of course, as any energy, right? It's a scalar. What can we say about the sign of v of x? It's positive or 0, right? As this equation clearly indicates. And when is v of x equals 0? Well, we have a sum of squares and fourth powers, right? So if it's 0, it's all these terms are 0, okay? So it's 0 if x, the vector, equals 0. In other words, if both position and velocity are equal to 0. Right? So it's a scalar function. That's the real energy, right? It's a scalar function which is positive and which is 0, takes its minimum value only at x equals 0, which is our equilibrium point. Okay? Okay. Now, questions about that? Okay, now suppose that we compute the time derivative of v of x. Right? So in other words, how energy changes as time goes on. Right? What are the units of this time derivative? Units of power. Right? Time derivative in energy. So the time derivative of v of x, well, it's mx dot x double dot. Okay, that's the first term. What's the time derivative of this term? Well, maybe we can look at it this way. It might be, well, more in general, we'll look at it more this way anyway. What's the time derivative of this term? Well, the integral with respect to x of something, okay, and we take the time derivative with respect to that, okay? So you have the chain rule, right? So the time derivative of this with respect to x would be what? Would be just the parenthesis, right, computed at x. Okay, so this would be the time derivative of this integral with respect to x. And you have to multiply it by the time derivative of x with respect to t, otherwise known as x dot. Right? So this is just the chain rule, right? So it's the product of d over dx times dx over dt. All right? So if you put everything together now, this x double dot, right? So this mx double dot, to be more precise, okay? We have it up there, okay? So it's minus b x dot absolute value of x minus k0x minus k1x cubed. And then we have the second term, k0x plus k1x cubed x dot. Right? Everybody followed that, right? This is just mx double dot. It's the equation of the dynamics, mx double dot equal. Okay. Okay. So, at this point, what can we do? Well, a miracle happens, right? We have this term, minus k0x minus k1x cubed x dot, which is exactly canceling that term. Now, it's not quite a miracle, right? Because in a sense, that's what potential energy is about. Okay, but, you know, it's good to be in a good mood, right? And so what's left, therefore, is x dot times minus b x dot, absolute value of x dot, which, if you insist, you could also write as minus b x dot q. Okay? So that's the time derivative of the total energy. It's equal to this. Now, when you do math, even simple math like this, you know, good advice is always to be as lazy as possible, okay? Because generally, you might have better ideas, okay? So if you were really lazy, and we'll see many examples of that, if you were really lazy, you would have dispensed from all this calculation and gone directly there. Why? Because of the first law of thermodynamics, right? You know, energy is conserved, right? So what's the time derivative of the total energy? Well, it's just the power dissipated. right? And what dissipates power here, there's only one thing that dissipates power, it's the damper. Okay? So this is simply power dissipated by the nonlinear damper, in other words, here the drag term. Okay? So we didn't really have to do this calculation. We could directly have jumped here and said it has to be that. Okay? And what can we say about this, right? It's always negative. Makes sense, right? The energy keeps being dissipated. And this time derivative is 0 if and only if x dot equals 0, right? If and only if the velocity is 0. Now, does this make sense? Well, think of this mass spring damper, or think of this, you know, this is pretty much the same thing, like a mass spring damper, except you have some singularities, okay? Think of the system. Why does the energy instantaneously starts being dissipated when velocity is 0? Because simply you're changing directions, right? So when you change directions, you know, at that time you don't dissipate energy. Okay. Now, incidentally, and we'll see much more of that, right? But I could have very well have started with this mathematical equation without telling you where it came from. And, you know, if you're mechanical engineers, you might have thought about mass spring dampers, or electrical engineers, you might have thought about something else. Economists, you might have thought about something else, right? But this whole calculation we could have done even if it wasn't a mass spring damper system, a physical mass spring damper system. It just needs to have these equations, right? And so in general, that's going to be also very much happening in Lyapunov theory. In other words, we're going to look at a system, x dot equal f of x, which comes from somewhere, and we're going to say, well, this could be a mass spring damper system, or this could be a robot, and if it was, then its energy would be. Right? Because the math are the same, the calculations are the same. Okay? Questions about that? All right. So we're almost at the point where we can start talking about Lyapunov theorems. Before that, I have one or two more remarks to make. So suppose we have a scalar function v of x of the state, all right? This function is said to be positive definite if v of 0 equals 0 and v of x is strictly positive for non-zero x. Now, you can have this definition locally or globally. In other words, it's locally if this is true in some region around x equals 0, and it's globally if this is true everywhere. Okay. So for instance, if the state is one-dimensional, then if you had a function like this, suppose this was v of x, right? Then this function, maybe we can just for fun, we can do this here. Then this function would be, and could very well actually go negative if you want. This function would be positive definite in this region. Okay, so it's 0 at 0. It's strictly positive everywhere. Okay, in this one-dimensional case. Now, in all of these Lyapunov or Lyapunov-related results, as you'll see, they are very simple results, but one should not make them simpler than they are. One has to be careful about, you know, the use of words and the use of inequalities and so on. Okay. So, just to give you an example, suppose you take a mass spring damper system, for instance, okay, a second-order mechanical system. This is the definition of a positive definite function. Is the kinetic energy a positive definite function? So who thinks the kinetic energy is a positive definite function? Okay. Who thinks it's not? Who couldn't care less? So the kinetic energy in the second-order system, right, is not a positive definite function, right? Because it's certainly positive, and it's 0 at 0 velocity, but it doesn't tell you anything about position. Right? It's not 0 at 0 velocity and some specific position, let's say 0, right? It's just 0 at 0 velocity. So for instance, this gadget here would be a positive definite function for the system. The total energy, the sum of the kinetic and potential energy. Right? But the kinetic energy by itself is a positive function, but it's not a positive definite function. Okay? All right. And last point, last kind of preliminary point. If we have a system x dot equal f of x, remember I told you we're going to define autonomous system x dot equal f of x and non-autonomous system x dot equal f of xt. So if we have an autonomous system x dot equal f of x, and we have a scalar function v of x, well, d over dt of v of x is equal to dv over dx times dx over dt, right? Always the chain rule. Right? So it's a function of x alone, so it's dv over dx times dx over dt. And because the system is autonomous, dv over dx, of course, that's just a function of x, because it's just a function of x, and so it's derivative with respect to x. Okay? But dx over dt, because the system is autonomous, is just f of x. Right? If the system was not autonomous, it would be f of x and t. Right? So why am I saying all of this? Because if you have an autonomous system and a scalar function v of x, then v dot is a function of x alone, not of time. And therefore, you can write it as v dot of x. Okay? So hey, if you have an autonomous system, and actually that's the basis of the proof of these Lyapunov theorems for autonomous systems, if you have an autonomous system and I give you a scalar function v of x, in other words, at any point in space you can compute the scalar value v, then at any point in space you can also compute v dot. You can compute the velocity if you want of v. And that depends only on where you are. It doesn't depend on time. Right? So if you have an autonomous system, the time derivative of v is simply v dot of x. Okay? Is that clear? Okay. So we're now ready for the first theorem of Lyapunov. So it's theorem 3.2 on local stability. So suppose you have a smooth scalar. Again, smooth means you can take derivatives, partial derivatives, and so on, and whatever you take exists and is continuous. So a smooth scalar function v of x. So you have a system, of course, x dot equal f of x, right? And our usual assumption that we're looking at the equilibrium x equals 0. So suppose you can find a smooth scalar function call it v of x. In all of this will be in some ball, call it b sub r0. So locally in some region. You can find a smooth scalar function such that this function is positive definite. And v dot is negative semi-definite. Okay? So it should be fairly obvious, but let me explain what I mean by this, right? So positive definite says v of 0 is 0 and v of x is positive for x non-zero. So that's positive definite. All right. Negative definite says the similar thing, of course, but for negative. Okay? So it's v0 equals 0 and v of x strictly negative for x not equal to 0. So that's negative definite. Positive semi-definite just says, you know, there's nothing special about 0. Okay? So it just says v of x is positive or 0 for all x. And negative semi-definite is v of x negative or 0 for all x. Okay, so it's fairly obvious extensions of the definition, right? So positive definite, strictly positive except at 0. Negative definite, strictly negative except at 0. Positive semi-definite, positive or 0 everywhere. Negative semi-definite, negative or 0 everywhere. Okay, so let's get back to this. So suppose you can somehow find a smooth scalar function, v of x, which is positive definite in terms of this equilibrium, right? V dot is negative semi-definite. Then x equals 0 is stable. This equilibrium point, x equals 0, is stable, of course, in the sense of Lyapunov. If more precisely v dot is negative definite, of course it's more precise because negative semi-definite just says it's negative or equal, it's less or equal to 0, and negative definite it says it's strictly negative except at 0. Okay, so it's more precise. So if more precisely v dot is negative definite, okay, then x equals 0 is asymptotically stable. Okay? So The theorem says you have three assumptions. One is that there is some scalar function that you found. Okay, the theorem doesn't provide it. We'll come back to that. Okay, some scalar function of the state that you found, which verifies two properties. It's positive definite in some region, and v dot is negative semi-definite. And why can we say v dot is negative semi-definite? Because v dot depends only on x, right? So if these three conditions are verified, then the equilibrium point x equals 0 is stable. If v dot is not just negative semi-definite, but actually negative definite, the only place it's 0 is at 0, then the equilibrium is not just stable, it's asymptotically stable. Okay. And so we're going to prove this, okay? So this is a local version. There'll be a global version as well, okay, which we'll state. And you'll see in the context of the proof that the nice thing also is that it tells you where from, you know, what is small r0, what is big r0, all these things, okay? What is the region where, you know, if you start from there, you get back to 0 and so on. Gives you the mechanism to find explicitly these regions. Okay. So let me explain the proof. We only have 5 minutes left, so let me explain the principle of the proof. It's actually very quite easy, and at the same time it's an extremely elegant interplay between geometry and dynamics. Okay. So what do we want to show? Well, let's show the first part, and then next time we'll show the second part. So what do we want to show? We want to show that if these conditions are verified, then for any ball of radius capital R, at least in yet bigger ball of radius R0, okay? So from any ball of radius capital R, there exists a smaller ball of radius small r such that if I start in the smaller ball, I never get out of the big ball. Okay? Now, this actually is in a sense quite easy to show because you start with this ball of radius big R, okay? And you define, let's say, call it M, is the minimum of v of x on the sphere, right? So on the shell of this ball, right? And for the mathematically inclined among you, right, the sphere is a compact set, so the minimum exists and is reached on the sphere. Okay? Now remember, R is strictly positive, right? So this minimum, which is the minimum of v of x on the sphere, since v is positive definite, in other words, it's nice and smooth and it's 0 only at 0, then M is going to be strictly positive as well. Right? So you start with this arbitrary big ball. You look at the minimum of v of x on this big ball, and you call it M, and you have a positive number, perhaps 17. Okay? Now, you also know that at the equilibrium point, v is 0, right? Because we assume v was positive definite, okay? So v of 0 is 0. Okay? So suppose this M is 17, right? V is 0 here, it's nice and continuous and can only be strictly positive, okay? So in other words, there's an entire region around 0 where v is less than 17. Okay? There's an entire region around 0 where v is less than this minimum M. So maybe it's like this. Okay? And of course, in this region, you can pick the largest small ball. Call it R. Okay? So the little cloud I did is the region where v of x is less than m. Okay? And this region exists, right, because v is 0 at 0, and then it varies continuously. So suppose now you start in the small ball. You have a trajectory, right? And it does things. And you want to show it never gets out of the big ball. Well, at this point, it's reasonably obvious because we started with the big ball. We constructed this small ball. Anywhere in the small ball, the value of v is less than the minimum value on the big ball. Right? But what else do we know about v? Well, we know that v dot is negative semi-definite. In other words, that v dot is negative or 0. In English, that v can only decrease. So you start here with a value less than m, or value less than 17, and v can only decrease. So you'll get values which are even smaller than m. And therefore, there's no way you cross out, because if you crossed out at the point where you cross, you would have a value larger or equal to m. Right? Because v can only decrease, it can never get back to the heights of v that you had on the big ball. Right? So you see, it's a very, I'll invite you to think of it over in your head, by the time, well, generally you think in your head, but to think of it by yourself by next time. It's a very, very simple idea, okay? But very elegant. You start with the big ball. You find the minimum of v of the big ball. Since v is 0 at the center, you find the whole region around there where v is less than that. You find the biggest ball in that if you want to be clean. And then whenever you start there, v can only decrease, so it will never be larger than m, the minimum of the big ball. And therefore, it cannot possibly get out of the big ball, because to get out, it would have to take a larger value. Okay? So that's the story about the first part of the theorem. We'll see the story about the second part is even simpler in some sense. Okay? And these are these very basic ideas from Lyapunov, very simple, elegant interplay between geometry, all these balls that you build, v of x, right? To talk about v of x, you don't talk about the dynamics, right? And then what v of x does based on f of x, which is v dot. Okay? So next time we'll prove the second part, which will be very quick, and then we'll give physical examples.